My name is Katya Prince, for those of you I have not met. I am Prince Consulting. I'm out of Durham. I've been programming in LabVIEW like forever and a day, and I've been doing consulting work actually since about 1998. In that time, I have done hundreds and hundreds of different LabVIEW applications and dozens of different lifecycle testers for various manufacturers. So what I'm going to talk about today are some of the issues and things you need to consider when you're deciding you're going to put a lifecycle tester together, and some of the, a few tricks, tips, and pitfalls. So the first thing I'm going to do is define exactly what I mean by a lifecycle tester. And sort of in the name itself, it's just going to be any sort of system that's going to cycle a product, some sort of a device, for an extended period of time, and often you take it until when the device actually fails. There's a lot of different reasons why you would want to do this type of a tester, and usually in manufacturing, there's sort of two extremes of a lifecycle tester. One would be if you're working on a brand new product and you need R&D to try and understand how your device is going to behave over time. You need to characterize it and get detailed information about what's happening to it over time. The second thing you might want to do is do industry qualifications. There's lots of industries where you have to give them statistical information, mean time to failure, that type of information. And so those are going to be sort of the two types that I'm going to discuss today. There are other reasons why you'd want to do life cycle testing, but that's what I'm going to focus on today. In both of those types of testers, there's going to be two main considerations that you need to bear in mind. One is the fact that this application is going to be running 24/7. The other one is that because of this extended time of testing, you're going to want to try and build a system such that you can test multiple devices at the same time. It's just, you need to get it the throughput as much as you want. So other assumptions on this talk is I'm going to be talking LabVIEW. We're going to be assuming that's what you're putting together. Most of my applications have been built on PCs with a Windows environment. So some of the things I'll be talking to are specific to Windows. And then the assumption is that while the main application runs on Windows, we may be communicating with other external hardware, be that a CDAC or a CRIO or any sort of standalone rack and stack equipment. So with that, let's talk a little bit about my example for you for this talk. I have a customer that makes thermoelectric devices. And if you don't know what that is, basically it's a cool little piece of electronics where if you apply a voltage or a current, you get a temperature differential between the two sides. It's used in a lot of different applications. There's pros and cons to it. We won't get into that, only to say that these customers were using it in a cooling application. And when I first started working with them, they were trying to design this device, and so we were into the R&D production, right? So we have a new product. We need to build a system that will be able to get information about that device. The other place you might want to use it is if you already have a device and you're making some sort of functional change, like I'm going from a brass component to a plastic component, you're going to want to run it through that lifecycle tester to see how does it behave over time. The goals of an R&D or production lifecycle tester are going to be that you need to have these things running in parallel. Usually you have engineers that are going to be driving this system, and so you need to have the flexibility to take the part off, start and stop each one individually, change the settings based on what you're interested in, and then be able to collect, like I said, detailed information about the DUT. And a lot of times people will cycle things for 10 or 15 times and then do a more detailed analysis on that part. So in the example of this thermoelectric device, when we were putting together the R&D lifecycle tester, we had the DUT there that in the middle that was orange. And for each of the DUTs, we had a specific power supply, an individual power supply. They had a voltmeter on it as well so that they could take some measurements. There were a couple of thermocouples on each one of those so that they could actually measure how the device was changing temperature across it. They each had a temperature-controlled base plate. You sort of need to control the environment, so you sort of need to maintain sort of a baseline temperature and then be able to measure the differences. But you can see that in this drawing here, we had what I would call shared resources. So we don't need to have a DAC for those two thermocouples. We had them going to a 32-up tester. And then in order to do the control of this base plate, there was a single chiller in the system that basically chilled the water that all of the devices used. Later on, once they had their device and it was ready for production, we had been testing them, they were considering maybe putting it in automotive or aerospace, so they needed to basically be able to qualify it for multiple devices. The goal to a qualification is we know how the device is going to behave, so now what we're really doing is we're trying to stress it to the point that it's actually going to fail, and then take that information to be able to create statistical information about the product, mean time to failure, that kind of stuff. So in this case, the hardware that we used, rather than having each DUT tested independently, they built a system where all of them were tested in series. And when we do that, you can have one power supply, maybe one voltmeter. You still need the base plate, and you still need a couple of thermocouples, and those were used more just to verify things were not going awry. And then you can see that in this system, we also have these bypass circuitry. And what's happening there is that if a device fails, you basically use a relay to switch it out of the system, and you continue testing all of those devices. So the idea here is you're looking at that whole batch, and as devices fail, you continue testing until you decide to stop it, or some sort of, all your devices fail, or something like that. So let me start talking about what you need to consider when you're building something that's 24/7. You're going to want to build your systems with minimal user intervention. You don't want to have dialog boxes popping up waiting for the user to do some sort of feedback. The system needs to be built so that it knows what it needs to do or makes its own decisions. If there's a failure, maybe it pauses, whatever it needs to be. You also need to consider that this is going to be an application that's going to be busy the majority of the time. You know, you could think like, oh, well, I built a little tester in the test lab. That's running all the time. But realistically, until the user hits a button, it's sitting idle the majority of the time. So bear that in mind in terms of CPU usage. And when I'm talking about some of this 24/7 stuff, it is not specifically, I mean, lifecycle testers run 24/7, but there are other ones that also do production line testing and any sort of process control. So any of the things I'm going to be talking about should be usable in those applications as well. Okay. Key to something that's running all the time is that you need to build for the whens, not the ifs, right? Anything that you think might happen will happen, and you need to consider it. The key, probably the easiest one that happens most often and is easiest to fix, is power interruption. I live in North Carolina, and in the summertime we have thunderstorms, and in the wintertime we have ice storms. So it's guaranteed that sometime during the year we're going to lose power. Luckily, that's easily mitigated. If you put a UPS on your PC, you can build the software in to detect you have a power loss, and then do things like maybe pause your testing, put everything in a safe state, and then wait for power to be restored. If you have unsafe or critical situations, and this obviously is going to depend on your particular application, but it could be something like, is something going to go over temperature? What are you going to do in that situation? If you're using a system that uses air or water pressure, what happens if that goes away? Or what if you have external equipment failure? In the example I'm showing, there's a chiller, and if the chiller water level goes too low, it goes into fault, and you basically have to stop the system because the chiller's not running anymore. The way you would mitigate any of these would be, obviously you need to detect it for your particular application. You can do alarming to look for things like over temperature, and then you're going to want to pause the testing, put it in a safe state, and in this situation, instead of having it automatically restart, you're going to wait for user intervention. The next thing that will happen is you will get communication loss with your external equipment. This is especially like, any sort of power supply or something like that. The way that I mitigate that is to have some automatic retries. Try to talk to it 2 or 3 times before you then go into the safe mode. Again, if you can't talk to it, and the reason why you might not be able to talk to it could be something like the power supply. If your power is lost, you may not have that device on a UPS, you lose communication, you sit and wait, and then once everything comes up again, you restart. Network communication, that's a big one that will undoubtedly happen. If you're doing things like putting files or a database to a remote server, you will lose communication. IT will decide that it's Thursday at 4 a.m., we're going to reboot the server. And so you want to be able to deal with that. You're going to have to do a couple different things, but you basically want to detect that. And if you are storing data, you may want to build a routine that stores things locally, and then once your connection is remade, go ahead and send that back up again. Similarly, you actually may want to retry a couple of times before you decide that you don't have any data, don't have any connection. The next thing to think about would be what happened if the PC dies, or your application crashes, or Windows decides to reboot, or critically, you have a hard drive failure. This is going to require a user intervention. So what I would suggest is that you build into your system some sort of system action logging so that you leave the breadcrumbs behind, so that if somebody has to come and figure out what actually happened, what was going on, they have that ability to debug. Make sure you create reinstall files and instructions. I've been burnt by this one way too many times. I've done so many projects that it's not unheard of that I get a call that says, our hard drive died, we're reinstalling this on a new PC, what do we need to do? And then I have to rack through my brain. And so now, even if the user is not gonna, even if my customer is not gonna pay for it, I'm still gonna create a little install cheat sheet that says, okay, it's using this hardware, you need to go into Macs and do this, that, and the other to get them up and running a lot faster. The other thing to consider is if you have mission critical control of hardware, consider actually doing maybe all your hardware control on a CRIO, and then you can build in logic so that if the PC application dies, that the CRIO basically recognizes that, puts everything into a safe state, and then waits for your PC application to kick in. Similarly, you could do the same sort of thing either with an external watchdog timer, master control relay systems, so that again, if something happens with the PC, the application dies, you can actually put the system in a safe state. Okay, so with that, let's actually switch a little bit and talk about hardware communication and some of the tips for that. I did a quick poll at the table, and they all agreed, no USB. Do not use USB, no matter what. I won't say avoid USB anymore. I'll just say don't use it. It's a very fragile bus. It's very easy to corrupt. LabVIEW can have a hard time trying to reestablish that communication. So especially for anything that's going to be running this long, don't use it. Find another way. Build in retries. Again, I'm just some of the stuff I'm going to be reiterating, but don't assume that the first time you can't talk to the hardware that there's a problem. Try to talk to it 2 or 3 times. Put a little delay in. And some equipment, like I said up here, if you're not talking to it, frequently, like a power supply or something like that, some of these instruments, especially the older ones, sort of go into a sleep mode, and you have to ping it a couple of times before it wakes up. If you are going to be changing settings, like on a power supply, you should read back the values to verify. This really depends on your driver, and it's a bigger deal with some of the older serial drivers because they didn't necessarily respond. So you could send out a write, and yeah, the serial port's there, the write's all good, but if there's nothing on the other end, it's possible that you aren't doing what you think you're doing. Okay. Let's switch to memory management. So this is something that's going to be running 24/7 for days, weeks, months, years. So you want to try to avoid doing a lot of array manipulation, anything that's sort of resizing. Things have gotten better, but still, doing this, building, resizing, anything along those lines is going to fragment memory over time. So what you want to do is use something like this little tip that I have here. A lot of times I'll use something like this when I'm doing arrays, if I'm creating charts, or if I'm doing running averages, where after I get to a certain size, I didn't write this, somebody else did, and I think it's the coolest thing. If you replace the first element and rotate the array, you're now looking at the latest 10,000 points, and all of this is in place, so there is no building and then truncating, or building or truncating, or anything like that. So you're saving on space, right? The other thing you're going to want to do, a lot of people will have like status strings on their UI. Make sure you're truncating those. Make sure that you're only looking at that, like the last 10,000 lines or something like that. You don't need to have everything from the beginning of your test. The other thing you need to do is to keep track of your references and make sure you're closing them if you're doing a lot of VI server type work. I never remember which ones you have to close and which ones you can ignore, but luckily when I was writing this talk, I came across this NI paper that lays out, these are the ones you need to worry about, these are the ones you don't need to worry about. And memory management, it can be the trickiest one. It's the hardest one to sort of test and debug. So there are tools that can help you out with that. If you go under Tools Profile, there's a whole series of different tests and tools that can allow you to statically analyze and dynamically analyze your VIs as you're running. Okay. So let's switch to, that's general memory management. Now let's talk a little bit more about files and data tips and tricks. This is going to be running 24/7, so you can't do something like, I'm going to save all the data and then log it at the end. Save as you go. Don't wait for things to be stopped. Break up those files. It's tempting to say, I'm going to send all of this information about a given DUT and store it in one file. If it's going to be running on the order of, again, days, weeks, months, you want to break that up based on size or time. And again, the other reason why you might want to do that is that you don't want, if the file for some reason gets corrupted, you don't want to lose all your data. And when you're designing it, you want to sit down and actually calculate how much data you actually will be calculating or creating and wanting to save. It's one thing to say, well, I have this one test, I'm going to collect it at 100 kilohertz. Well, 100 kilohertz times 10 seconds times 5 times a day times, you have to start calculating that to make sure that you're not going to run out of space. Hard drive's not as big a deal, but the database, you need to consider that you're going to have enough room in your database for that kind of stuff, if you're doing that. And again, don't keep everything in memory. You don't want it in your application. You're usually going to be running these things in sort of like a step, like I'm going to cycle it once, and then I'm going to collect data, or collect it, do what you need to do with it, and get rid of the raw data. Let's talk a little bit about the PC itself. Some of this you may have a tough time doing. Sorry, I'm going to lose track of talks, but the idea of that Windows is updating once a month now, right? You want to try and disable all the auto updates and restarts. You're probably going to have to talk to your IT department and maybe come to an agreement to say, okay, on the third Thursday of the month, we're going to pause everything and then do all our updates. You want control over that. You definitely don't want it deciding to restart your system again at 4 a.m. on a Thursday. If you're doing a lot of file I/O, disable file indexing. That can get in the way of reads and writes. And same thing with automatic defrag. Windows still comes with that installed, defaulted to be once a week. Defragging the hard drive, and SSDs are different, but defragging the hard drive can, again, get in the way of reading and writing files. Okay. The next thing I'm going to talk about are LabVIEW licenses. And this is, again, talking from experience here. Be sure you use an EXE. Do not leave them with a VI, with your subscription that expired in August, and then they rebooted the computer in November, and now the application doesn't work because the license has expired and needs to be reinstated. Use an EXE. Similarly, some of these applications will need deployment licenses to run, like Vision or OPC, test stand as well. Use the deployment license, because if you use a development license and the subscription expires, the system's not going to work and the customer's going to be mad. So just a little word of warning there. When you think about building this operations, a 24/7 application test stand, put in some pausing and resuming. It is not uncommon for them to test a part for a month and then want to pause the testing, take the device off the tester and go and do visual inspection or maybe some other testing, and then place it on the tester and resume testing. Make sure you're updating the user interface with information. So even if you have a tester that says, I'm going to do something and then wait for 10 minutes and then do something else, give them that feedback so that they know that something is actually going on. Never use a millisecond wait longer than a second or two. This just causes everything to slow down. It responds incorrectly. The users don't know what's going on, and you'll Control-Alt-Delete out of your program when you don't want it to. And reiterating again, update your results as you go. If you've run 10 cycles, make sure that you maybe create a status file and a temporary file so that, again, if the system crashes altogether and you want to restart, you can maybe bring that back up again and say, okay, we've done 10 cycles, now we're on cycle 11. So with that, that sort of covers what I'm going to discuss about 24/7 operation. I'm sure there are other things, but that's what I'm going to talk about today. The next thing I'm going to talk about is the idea of how do you run multiple DUTs at the same time. In the R&D, you want each DUT to basically be tested in parallel. And in qualification, the DUTs are usually batch tested. And so when you develop your software, I'm going to show the qualification first and then the R&D second. But when you're designing the software for qualification, you may do something like this on the left, where each one of those blocks could be considered an actor, a QSM, an engine, whatever you want to call it. But they could all be running sort of in parallel with each other and communicating back and forth. Or you could basically have some of them running in parallel and then have what I'm calling the test step engine, which would just be what's controlling how the system works. And you may have something where they control everything as like a driver instead of maybe an engine. Either one of these is equally valid. It really just depends on what you're familiar with and what works best. In the case of doing parallel DUT testing, you may have these, I'll call them shared resources running in parallel. But then you want your main application to dynamically launch each one of your stages. And when you're designing things, what you need to consider, like whether that information is going to go within the test stage or whether it's going to sit here on that main level, is going to be a question of what is a shared resource and what is an individual resource. And so in the example that I was showing, we saw that the 32TC DAC card, that could be considered a shared resource and would live here. Similarly, the chiller controller would also be sort of sitting there. They all need to talk to it. But there are other possible shared resources that you might not consider. A key one is your communication bus. GPIB inherently is not shareable, right? So if you're using GPIB to talk to your equipment, instead of being here with each test stage, you may actually have to have a GPIB engine that runs in the main application. Same thing with RS-485. Other things you can consider to be shared would be things like error logs or system log files, and maybe even configuration files. So the question may come up of how am I going to, sorry, getting distracted here a little bit. How am I going to build my tester, these individual stages? And the way that you're going to do it is by using reentrancy. And does anybody here not know what reentrancy is? You all do. That's so awesome. So what you can do, I won't even go into the definition necessarily, but what you can do, rather than having to create individual VIs for each test stage, you can basically create one VI that's reentrant and then have it dynamically launched. And with every dynamic launch, you're basically creating its own stage. So here's an example launcher. I built this for a queued message system, a queued state machine type of application. So you can see you had coming in, we have the number of stages we want to run, and in the middle there and under 2, you create the queues that you need. You maybe push to each one their initialization message, and then you can see you open up a reference to your reentrant VI, pass data in, and basically start it running. You run and forget, and so basically you're left with the references that later on you can use to bring into a subpanel to show the front panels. Down below here under 4 is just user feedback. This is letting them know that where am I in my loading process. The thing to remember, of course, is that that test VI, that test stage VI, has to be reentrant all the way down. If a reentrant VI calls a non-reentrant VI, you've lost all advantage of that reentrancy. Another thing to note is that most device drivers don't come out of the box reentrant. So this accounts for your Agilent devices and things like that, and it kind of makes sense because they originally, way back in the day, were built to run on a GPIB interface. So you may need to go in and rewrite some of them, or at least rewrite the components that you need. You probably won't need to do everything, but there may be some keys. The other little tip that I found, just like last week or something, is that VI Analyzer actually has a test for reentrancy that will flag when you have non-reentrant VIs inside of reentrant callers. And even with all of this reentrancy, there may still be situations where you don't want it to be reentrant, like some sort of a user dialog box. Rather than having 27 of them show up, you may want to show them one at a time. And so you still may want to have things be non-reentrant. Okay. So now what I'm going to do is just talk about, we could have a fight, I suppose, over to which package is going to be the best for creating this lifecycle tester, but really it's up to you. You can, anything that you're familiar with, you can use to create a lifecycle tester. UI suggestions I would have is to have part of the screen be summary information telling you about what's happening on all the stages at once, and then have detailed information in another section. Include some sort of a pause all, resume all, stop all, that type of thing. If you have 32 stages, you definitely don't want to have to go through and click each one individually if you need to do something like replace a water line or something. And try to build your system with extension in mind. So like what I showed you there, where we launched however many number of stages, that was from an INI file. So if I have the hardware available, I could set it up to run for 4. And if we had the hardware available, I could set it up to run for 16. But it's not going to be limited by the software. So here's an example of a UI where I'm taking that into consideration. On the left-hand side, we have general system information, and we have information, sort of summary information about what the status of each stage is. So you can see here that stage number 4 is paused. And then when I click on that, I get the detailed information about a given stage on the right-hand side with information about how many cycles have been run. Maybe there's a trending plot that shows the temperature over that time, something along those lines. The last thing I'm going to talk about is troubleshooting these applications. There's going to be two main things that'll happen. Most likely, obviously, there's other possible things, but these are the most common issues you're going to run into if your application continues to grow and grow and grow, and this is true of all LabVIEW apps. Most likely, you have some sort of unbounded array or a string that you're not truncating, or you have unclosed references. The other behavior you might see is that, oh, it works all great if I'm only running one stage, but now I run the second stage and everything slows down. The UI's not updating, things just aren't working correctly. And the most likely reason is that something down below in your application and under the stage is non-reentrant. So with that, I hope that I've given you guys an overview of the types of issues that you're going to need to deal with when you're running a lifecycle tester, and I would be happy to take questions. Thank you.
Hi, I'm asking for a friend, but you mentioned don't use USB. Can you elaborate on that a little bit?
Okay.
Like you said it was fragile in particular. What do you mean by that?
Right. Well, so there's a couple things that can happen, and maybe things have gotten a little bit better, but there was at least one application I had where if a user pulled a USB drive without undocking it, it would basically corrupt the USB bus, and then what would happen is all the devices would drop out, and then they would come back on again. And what happens in that re-enumeration, at least at that point, was that any of the DAC devices, that connection was lost. LabVIEW could not reestablish it without actually restarting LabVIEW. That's one of the issues that can happen. The other thing can happen if you're using like USB to RS-232. Because there's no serial a serial number associated with them. You've probably seen this, that the COM port that it decides it's going to be will change based on where it's plugged in, and that has to do with how it's enumerated. So if something happens and it gets enumerated differently, now instead of COM1, COM2, you're dealing with COM3, COM7, stuff along those lines. So both of those can happen, and that will obviously get in the way of your program.
I'm going to jump in and help you out too, because we've actually had a system, like Tektronix scopes are kind of, we've had problems with them because they hook up by a USB, but like after a certain amount of time, they would stop working. And then you had to reboot the whole scope in order to get the USB back. And so because they come with Ethernet, just use that.
Yeah. And the other thing, too, is that nowadays you can get, I've been using these a lot, there are now Ethernet to RS-232 servers, and those work really well because now you're dealing with Ethernet connections, and you configure them. They're a little less flexible because you can't configure the COM ports. Maybe you can, I can't. So those become sort of static, but at least you don't have to worry about them dropping out.
I will also add chipset matters, especially if you're using USB hubs. For one of my clients years ago, we were doing a USB hub to more than 196 USB devices with chain cascade, and certain manufacturers worked very well. Certain manufacturers, forget it.
Yeah, so I had another application where they were doing sort of cascading, and then what ended up happening was that they didn't all enumerate in the same order every time. So that was another issue that ended up happening. So.
Okay, I saw a lot of hands. Are there questions that are not about USB nightmares? Okay. Because I think just everybody that's had issues with USB devices, all right, that's why you don't use them.
Regarding network connections and temporarily logging things locally, and then, did you have any tips about that? Like in particular, I'm curious, do you typically have do you push the data out, and then when the connection is back, do you have whatever on the remote server pulling it off? How do you verify that the data has been copied in full, and do you
Right.
check checksums? Do you have any?
So I'm really paranoid about all this kind of stuff. So personally, the way that I usually build mine is I work exclusively locally. And then if I need to push data, I either will maybe take a file and put it in a different folder, and then have another part of my LabVIEW VI that basically pushes it up to the server, something along those lines. That's just because I'm paranoid.
How do you know it's made it to the server though? What kind of checks do you there? Because I'm always paranoid about like the internet connect or the
Right.
network connection going down in the middle of the
That's
transfer.
a good question. I've never. That's a good question. I guess the only thing you could do if you were doing something where you're pushing it, you could do something like check the size of the file and then only delete it locally once you verify that it's up there. That's about the only thing I can say for sure. I believe the other thing that I've done is I've depended on third-party apps that do that sort of transfer and stuff like that. So once LabVIEW's done with it, it places it in a folder and some other app takes care of it. And then I kind of assume that they take care of that kind of information. So, and the other thing too is that especially if we're dealing with like a relatively local network, once it's up and running again, it's going to be up for a while. It's usually, so trying to think of all the different things you could do.
I'm curious about how you funnel the support requests. So you said, that you have one of the fault conditions, you pause the system. Are you then sending out email alerts or calling people, or how does it then, is it waking you up in the middle of the night?
Well, luckily I take my email name off of that list. That really depends on what the client wants and stuff. And so I've built it both where it didn't do anything, and then it was just a question of what happened when they came in the morning. And there are other customers that already sort of have that in place, and I just reuse their code. So you get to a fault condition and it sends it out. I had that same client also would send a periodic status, and so that would be the other way. If you didn't get that status, you knew something was up.
So have you used Windows OEM versions? Because when you're at that level of like, you really need to keep it alive, it seems like Windows OEM would be a good solution.
I haven't used that, so I don't know. I just usually go with whatever they give me, and so I don't know what.
So
explain some more.
If you can get industrial PCs and basically get an OEM version of Windows where you select what are the parts of Windows that you want.
Right.
So you can get all the stuff that you don't need, and I'm going to be very obvious here, like games and stuff like that.
Right,
but you
right.
can remove
Sure.
even services that you don't need.
Right.
That helps you a lot with the updates, because when IT department goes and pings on it, it recognizes it as a computer, but it also recognizes that it doesn't need all the updates that the other
Right.
computers need. It is definitely a lot more investment. They are more expensive, but they're also easier to block the ports and all that. And then on the terms of I know you just said not USB, but the terms of the enumeration, I tend not to rely on the COM port. I do more like self-discovery, so either configure for the serial number of the device you're communicating with. You have some sort of, if you are developing the device, you put some sort of ID so you can know who you're talking to and don't rely on the COM port.
That's a good idea.
Yeah.
That works okay unless you have like radically different instruments, and then you're having to deal with like, am I talking to the power supply or am I talking to the voltmeter, and that gets just a little bit hairy.
Yeah, sorry. Any recommendations on benchmarking? Like what specific set of tool set will be your go-to? Like, do you use a combination? Let's say that your problem arises after 4 days, and it's not coming at the first day. Everything is working fine, right? But then
Right.
you work for 4 days, you don't know what's going on. So once everything is said and done, what would you use, or any recommendation of a specific recipe of tools that you use?
So I use a lot of the profiling tools, and what I might do is I might try to accelerate the testing to try and sort of, like if I know that normally the test was going to be, a cycle was going to take 10 seconds, maybe I'll say, okay, I'm going to now cycle it at 1 second and look to see what happens over time. I've found that in general, that if I have issues with memory getting too large, that's going to show up earlier. It's going to plateau, or it's just going to keep going. And if it keeps going after an hour or two, it's going to keep going. So I don't usually run into issues where it fails after 4 days. things like that could possibly because, if stuff drops out of the network or something like that. So, sorry, but I don't.
Yeah, so that's one of the specific cases that I was, why I asked this question is maybe somebody is saving into a OneDrive shared folder, and then your disk time gets really high, and now throughput gets down, and then suddenly you get errors where you were not having them before, and everything because of a folder. I use Performance Monitor. That's why it's what I would use is Perf1, and it's super useful, and it's on every Windows system.
Sure. Yeah, definitely for sure. So along with the NI tools, I definitely use the Memory Manager and the Performance Manager in the Windows operating system for sure. And look to see how big is my LabVIEW app getting, how fast is it, how much CPU it's using, that kind of stuff. Anything else? Great, thank you very much.